Hey guys, Steve from Vorsprung Suspension in Whistler here. Welcome to another Tuesday Tune. This week we are going to look at harshness and bump compliance, and basically have a quick look at the factors that affect those, so that hopefully you can understand a little better what adjustments you might want to make with your suspension and bike setup. There's a lot of factors involved in this. We're going to run through the theory behind what creates this harshness, so you can understand what you want to do in order to minimize that. So first things first, we'll have a look at a very simple case of single square edge bump where we're not worried about repeated hits or anything just yet. So in this diagram here, we have the initial wheel position, the black arc here being the outer circumference of the wheel, and that being the axle position relative to that wheel position. Then we have the blue, so the axle and the tyre there. So we have a constant velocity in this direction. What we're looking to do is move the axle from there to there. This vertical distance, as shown here, in that horizontal distance. What we're essentially trying to do is minimize the vertical speed of the wheel here. Vertical speed will lead to the highest high-speed compression damping rates, and that alone, the force generated there, can be sufficient to cause that harshness. So what we're ideally looking to do is have something that is, an axle motion profile like that. Now that isn't actually possible, given that the maths of rolling something up over a bump like that don't actually apply. And what you would actually get in a motion profile in the simplest manner is something that goes like this. However, what we're trying to achieve here really is just the minimization of the steepest part of that curve. So in order for the axle to get from this point here, above the ground there, to being directly above the highest point of the bump, it obviously has to be levered up by the wheel. If this was rigid and moving very slowly, you'd get something where obviously this is just pivoting around there. So that would end up being something like that. Now, in reality, we get deflection of the tyre, which is what gives us this kind of a profile. So this intrudes into the tyre. So if we then draw a displacement profile that matches that with vertical against horizontal. Now horizontal is also related to time because we're moving at a constant velocity. So where this becomes relevant is that this gives us our displacement profile relative to time. If we're moving at a constant speed, that horizontal distance that we travel can be correlated directly with time. So as we move here, the wheel starts moving up, and that thus compresses the suspension, obviously. Now what happens is that initially it starts from zero, you get some intrusion of the bump into the tyre, compresses the tyre, that loads everything up, starts to accelerate it, it accelerates to a maximum velocity, then slows down. And then at this point, obviously if we are looking at this as a suspension displacement rather than an axle displacement, then this will start to turn around and your displacement will appear to come back down because it's extending the suspension and lifting the rider up. So when the axle gets up to here and the suspension is at its maximum compression, over time the spring will lift the bike back up. So what is really important here is this point just there, which is essentially the highest velocity. Now if you imagine that you create some restriction in your suspension to the movement, and that can be friction, it's probably the biggest one, excessive low speed damping, or even a spring rate that is too stiff, especially early in the travel. What you can do is cause this to lag. And so that means that you still have to get this high up in this amount of distance. So the axle has to get up there. Now what can happen then is that if there is a lag in that that's caused by friction, the wheel doesn't move out of the way freely. Is that this then goes like that, but then in order to get up there, it has to move even more steeply. Now obviously I've drawn like an impossibly steep vertical curve here. That isn't actually possible. But it has to move very, very steeply. And that gradient there, as compared to this gradient here, this being steeper because it has to, at this point you have, instead of having this much time to cover that vertical distance, you only have this much time. Obviously, the average speed in there is going to be higher. That means higher damping forces, higher harshness transmitted through to the rider. And so what we're really looking to do is minimize that lag, get this thing moving as quickly as possible. So what we want in an ideal world is for this to start moving very quickly at a relatively constant speed. So we don't want it to be having to reach too high of a peak speed because it's essentially started the majority of its motion too late. We want it to start moving quickly, very early, so that we, in an ideal world, you'd have something like that, which obviously is going to have a much lower gradient than anything that comes out here or whatever it may be. So this is one of the main principles of reducing bump harshness. And so what this really comes down to is minimizing the initial resistance of your fork or your shock to motion. And so that basically means not having too much low-speed compression damping, not having friction that can be avoided, and even reducing your tire pressures as far as possible. So the role that tire pressure can play in this is, if you imagine this wheel was rigid, as soon as it gets to there, as soon as it reaches that point, all of a sudden the wheel has to be moving in that direction. And in order to get there, it has to accelerate at a ridiculously high rate. Now that alone transmits a lot of vibration through the suspension. And it's worth keeping in mind that when you have a suspension fork that is moving in this direction, you have your axle down there and the thing can move in that direction. Any force that you apply that is not parallel to the direction of motion of your suspension will induce some harshness because it essentially trips the bike up. So if you hit something that's at axle height, obviously you have a large horizontal component there. Likewise, a purely flat landing has a component like that, and that is essentially trying to bend the fork one way or the other. And the same thing happens with your with the rear wheel of your bike. Any motion or any force that is not acting directly through the line of motion of the suspension will have some sort of decelerating effect on the suspension as well, on the bike as well. And so that alone can give you a large sense of harshness, even though it isn't strictly vertical displacement, it's horizontal displacement, horizontal acceleration that you're feeling through the bike. The reason that tire pressures allow you to reduce that velocity is essentially that the tire can deform more and mean that this axle doesn't actually have to be above there. It can be above, it can only reach that height a little bit past the bump itself because the tire itself is compressed and giving you more suspension travel effectively. So reducing that lag is pretty critical. Now this is not the same as reducing the lag in a damper. Reducing the lag in a damper is almost the opposite of this. It's actually about giving you damping resistance as quickly as possible. That is usually more of a road racing thing. The reduction of hysteresis, less critical on mountain bikes. I'm not going to go into that to any great detail. One of the other things that can definitely cause substantial harshness is excessive high-speed damping. Obviously, when you hit square edge bumps like that, or any bumps where you're going fast and the suspension is moving very quickly, the high-speed damping has a substantial effect. Above a certain force threshold through the handlebars, a certain rate of acceleration really, we start to feel discomfort, pain, and that is really what we want to try and avoid crossing as a threshold. If you cross that threshold on a particularly big hit, a big single hit, you happen to send it 15 feet to flat by accident and you cross that threshold, it's probably worthwhile. However, we don't want to be doing that 400 bumps in a row down a line. If we look at the maximum velocity that we're realistically seeing on these types of bumps, anything that is repeated in particular, we want to make sure that the total force generated by your spring and your damper is not exceeding that threshold. Now, looking purely at the damper aspect here, because these velocities can be achieved in very short distances without necessarily building up a substantial amount of spring force. What we want to do is make sure that the high-speed damping is not simply so high that we are crossing that pain threshold readily and causing ourselves pain and discomfort in our hands, in our feet, whatever it may be. So that is where the realistic limit to your high-speed compression damping comes in. It just makes things painful. For most people here, this is going to be an exercise in theory more than practice. If you go for a high-speed valving that is too firm for you, it will essentially hurt. Now, so far I've talked about suspension velocities and forces coming through the suspension. Now, what really determines how you feel, the harshness that you feel, is acceleration of the handlebars or the pedals. Everything between the ground and there is extraneous to what happens at the handlebars. You only really care how far or how fast the handlebars are displaced. And so minimizing that is really what we're all about. Minimizing that acceleration of the handlebars. That is what causes the harshness. So that is the end game. What we are looking at is the systems in between the wheel and the handlebars, and how, between the ground and the handlebars I should say, and how they control that, the creation of that acceleration. So the spring curve can also have quite an effect on this. This blue line here being a completely linear spring curve, something like a coil spring will give you in a fork, or this red line here being a particularly progressive system, we have a certain amount of sag force. And so that sag is not necessarily our static sag, but like a dynamic ride height load that's being applied. And so that will tend to keep the bike riding at a certain height in its travel. Now, if you have a completely linear spring rate, in this case, you'll ride higher in the travel, you'll be less far into it, this being displacement and that being force. Whereas if you have a much softer initial spring rate, then you'll get more sag and you'll ride further into the travel. Now, in smaller doses, this is generally a good thing. Experience has shown us that some degree of progression in your spring rates is typically beneficial. If you take that to extremes and you're running, here it would be like 60% sag, something ridiculous. Then, for a given bump, you only have 40% of your travel left versus, say, 70 or 80%. Now, obviously, the spring rate in here is substantially steeper than the spring rate there. So that means that this will give you less compliance. The further you get into the travel, the stiffer it gets. And so it's very easy to find yourself just running into this wall of force, at which point there is less of that motion of the suspension and there's more vertical acceleration of your handlebars, and that can lead to harshness. And so the general idea that making things softer will reduce harshness is only true up to a point. There is a point beyond which it starts getting worse again rather than better. Now, we're looking purely at single bump situations here. In the case of multiple bumps, obviously the suspension has to be able to recover fast enough in order that you have a substantial enough fraction of your travel left that you're not running into that wall of progression in the spring curve in particular. If that happens, then things get very harsh very quickly. Now, this certainly is not a comprehensive analysis of harshness and hand pain and that sort of thing. There are a lot of factors that can cause that. Even the diameter of the grips you're using, the diameter of the handlebars, how stiff your handlebars are, your brake lever setup, your brake power has a huge effect on that, funnily enough. More powerful brakes give you a lot less hand fatigue. Anyway guys, I realised that was a fairly heavily theoretical exercise. However, hopefully it gave you something interesting to think about. Again, not intended to be an exhaustive analysis of harshness because it is a very complex topic and there are limitless things you can talk about. However, hopefully that is of some interest and some use to some of you. But that's it for this week, and until next week, we'll see you then.